Captain First Rank Viktor Antonov believes he is the apex predator of the Barents Sea, but in the freezing darkness beneath the ice, he is about to discover that the laws of physics he spent a lifetime learning have been broken by his enemy. He is being watched by a ghost that moves faster than sound should allow, a machine that defies the fundamental rules of underwater warfare. This is the moment a Soviet commander realizes that the ocean has become transparent, and there is nowhere left to hide. It is March 17, 1983. The time is 2:47 in the morning. The location is 300 feet beneath the surface of the Barents Sea, just 47 miles from the Soviet Northern Fleet headquarters at Severomorsk. The water temperature is just above freezing. The pressure against the hull is 130 pounds per square inch. Inside the pressure hull of the Soviet ballistic missile submarine K-424, the atmosphere is heavy with the specific mechanical tension of a strategic patrol. The K-424 is a Delta II class submarine, a 540-foot Leviathan designed for a single apocalyptic purpose. She carries 16 R-29 nuclear missiles in the large, humpbacked casing behind her sail. Each missile is armed with 7 independently targetable warheads. Captain Antonov knows the arithmetic of his command by heart. 16 missiles times 7 warheads equals 112 nuclear explosions. 112 cities could burn if he receives the encrypted burst transmission from Moscow. But tonight, Viktor Antonov is not thinking about the end of the world. He is thinking about ghosts. For the past 6 days, the routine of the patrol has been shattered by anomalies. The sonar operators, men trained to distinguish the heartbeat of a whale from the rotation of a screw, have been reporting strange contacts. They are faint, intermittent whispers that appear at the very edge of detection and then vanish before a firing solution can be calculated. Sometimes the sound seems to come from directly behind them, in the acoustic blind spot created by their own propeller. Sometimes it appears on the port quarter. Once, impossibly, it seemed to come from almost directly ahead, only to disappear as soon as the K-424 altered course to investigate. Antonov stands in the control room, bathed in the red tactical lighting that preserves his crew's night vision. He is a veteran of the Northern Fleet. He knows that the Barents Sea is a noisy place. The shifting ice pack overhead creates a constant grinding roar. The thermal layers trap and refract sound in deceptive ways. A novice commander might dismiss these contacts as biologics, schools of fish or marine mammals, or perhaps the echoes of their own machinery bouncing off the seabed. But Antonov is not a novice. He feels the prickle of instinct on the back of his neck. He knows that he is being hunted. To confirm his suspicion, he has already ordered 3 Crazy Ivan maneuvers in the last 48 hours. The Crazy Ivan is a desperate, violent tactic born of necessity. Because a submarine's propeller churns the water directly behind it, the sonar cannot hear anything in its wake. This blind spot, known as the baffles, is the perfect hiding place for an enemy hunter. To check the baffles, a Soviet commander will order a sudden, sharp turn, usually 150 degrees or more. The submarine heels over, engines roaring, swinging its bow around to clear the blind spot. It is a dangerous maneuver. If another submarine is following too closely, the result is a catastrophic collision. 3 times, Antonov has thrown his massive ship into a hard turn. 3 times, the sonar screens have shown nothing but empty black water. The ghost disappears the moment he turns to look at it. Now, deep in the mid-watch, the silence in the control room is absolute. The only sounds are the hum of the ventilation fans and the quiet clicking of the depth gauge. Lieutenant Sergei Volkov sits at the primary sonar console, his headphones pressed tight against his ears, his eyes scanning the green cascade of the waterfall display. Volkov is one of the best ears in the fleet. He has listened to the ocean for thousands of hours. He knows the signature of every NATO warship and every American submarine class. But what he is hearing now does not make sense. He removes his headphones slowly. His hands are trembling slightly. He turns his chair to face the captain. "Comrade Captain," Volkov says, his voice barely a whisper, "I believe we are being followed." Antonov steps closer to the console. "We have checked the baffles, Lieutenant. There is nothing there. How can you be certain?" "Because whoever is following us," Volkov replies, "just made a mistake. A very small mistake." The lieutenant points to a faint, almost invisible trace on the screen. "When we accelerated 20 minutes ago, the contact matched our acceleration. But when we slowed down just now, they adjusted their speed to match ours. The timing was perfect, too perfect. They are not reacting to us, Captain. They are shadowing us. Antonov feels his stomach tighten. What was our speed during the acceleration? We touched 22 knots, sir. And the contact? They stayed with us. Constant bearing, constant range. The implication of this statement hangs in the air like smoke. Are you telling me, Antonov asks slowly, that an American submarine kept pace with us at over 20 knots, and you could still hear him listening to us? I am saying, Volkov answers, that he was there, and he is still there. To a layman, this might sound like a simple game of cat and mouse, but to Captain Antonov and to every naval engineer in the Soviet Union, what Volkov is describing is a physical impossibility. It violates the fundamental laws of underwater acoustics as they are understood in 1983. In the world of submarine warfare, sound is the only currency, and the iron law of acoustics is that speed equals blindness. A submarine moving through the water generates noise from three primary sources. First, there is the machinery, the reactor pumps, the turbines, the reduction gears. Second, there is the propeller cavitation, the formation of vacuum bubbles that collapse with violent force as the blades spin. Third, and most importantly at high speed, there is flow noise. As a submarine pushes through the ocean, water rushes over the steel hull, it rushes over the sonar dome, it rushes over the hydrophones. This turbulent water creates a deafening roar that blankets the submarine's own sensors. The physics are merciless. Flow noise does not increase linearly with speed, it increases exponentially. Specifically, it increases in proportion to the speed raised to the sixth power. This means that if a submarine doubles its speed from 10 knots to 20 knots, the noise rushing over its own sensors increases by a factor of 64. At speeds above 15 knots, a submarine effectively becomes deaf. The roar of the water drowns out the faint whispers of enemy vessels. At 20 knots, the sonar is useless. At 30 knots, the submarine is blindingly loud to everyone else in the ocean while being completely unable to hear anything itself. This is why the universal tactic of submarine warfare is sprint and drift. A commander will run fast to cover distance, accepting that he is deaf and loud while he sprints. Then he will slow to a crawl, 3 or 5 knots, to drift and listen. It is the only way to hunt. You cannot run and listen at the same time. Yet Lieutenant Volkov is reporting that an American submarine has just done exactly that. If the ghost behind them maintained contact while the K-424 was sprinting at 22 knots, it means the American was also moving at 22 knots. At that speed, the American submarine should be deafened by its own flow noise. It should be blinded by the turbulence over its bow. It should have lost contact the moment the chase began. Instead, the American boat not only kept up, but it maintained such precise acoustic awareness that it could detect the K-424 slowing down and match the deceleration instantly. Antonov looks at the chart table. They are in the Barents Sea, the bastion of the Soviet Navy. This is supposed to be their sanctuary. If an American submarine can track them here at high speed without losing contact, then the sanctuary does not exist. Are you sure it is not a surface ship? Antonov asks, grasping for a conventional explanation. A destroyer using active sonar? No, sir, Volkov says firmly. No active pings, passive tracking only, and no surface screw noise. It is a submarine, a single screw, 7 blades. It is a Los Angeles class. Antonov nods grimly. The Los Angeles class. The Americans call them 688s. They are fast, rumored to be faster than anything except the Soviet Alpha class. But speed is not the issue here. The issue is the impossible combination of speed and sensory perception. If the Americans have found a way to listen while sprinting, they have broken the tactical equation that has governed submarine warfare since World War II. It means they can hunt down a ballistic missile submarine like the K-424 without ever pausing to listen. It means they can close the distance at 30 knots, set up a firing solution, and launch a torpedo before the Soviet commander even knows he is in a race. Antonov walks to the periscope stand, though he knows there is nothing to see. He grips the stainless steel handles. He thinks about the 112 warheads in the missile tubes behind him. Those missiles are the guarantee of his nation's safety. They are the deterrent. But a deterrent is only valid if it survives. If this American ghost is sitting in his baffles right now, undetected and undetectable, then the K-424 is already dead. The missiles will never leave their tubes. Captain, the executive officer asks quietly, "What are your orders?" Antonov stares at the bulkhead. He has a duty to shake this tail. He has a duty to prove that Soviet engineering is not inferior to the Americans. But deep down, a cold realization is settling in. The enemy is not just lucky. They are using a technology that Soviet science says should not work. "We will try again," Antonov says, his voice low. "Prepare for a depth excursion. We will go down to 900 feet. We will find a thermal layer, and then we will execute another crazy Ivan." The crew moves to obey. The diving officer barks commands. The plainsmen push their yokes forward. The deck angles steeply as the massive submarine begins to slide deeper into the abyss. But as the K-424 descends, Viktor Antonov knows that he is fighting a new kind of war. The old rules, sprint and drift, hide and seek, have been rewritten. Somewhere back there in the black water, an American captain is watching him dive. That American captain is moving fast, and yet somehow he is hearing everything. The ghost is real. And for the crew of the K-424, the terror is not that they are being followed. The terror is that they are being followed by a machine that seems to have solved the problem of physics itself. They are about to play a game of tag with an opponent who can see in the dark while running at full speed. The signal from Captain Antonov did not stay in the Barents Sea. It traveled south, encrypted and compressed into a burst transmission, bouncing from a communications buoy to a satellite, and finally descending into the gray, brutalist architecture of Moscow. It landed on a desk deep within the main naval staff of the Soviet Navy, joining a stack of identical reports that had been growing for months. This was no longer an isolated incident. It was a pattern, and to the analysts of the GRU's Naval Intelligence Directorate, the pattern looked like a losing war. In a windowless briefing room 3 floors beneath the streets of the capital, the air was thick with the blue haze of cheap tobacco smoke. It was the spring of 1983. The men gathered around the heavy oak table were not politicians. They were the technical elite of the Soviet military machine. There were admirals with chests heavy with medals, hydrodynamics experts from the Krylov State Research Center, and grim-faced officers from the KGB's First Chief Directorate. They were looking at a map of the world's oceans, covered in red pins. Each pin represented a contact, a Soviet submarine that had detected an American Los Angeles-class boat. But the data attached to the pins made no sense. The meeting was chaired by Admiral Sergei Gorshkov's deputy for intelligence. He picked up a file, the paper crinkling in the silence. "Comrades," he began, his voice rasping from decades of shouting over diesel engines. "We have a problem of physics, or rather a problem of American physics." He threw the file onto the table. It slid across the polished wood. Report from K-424, report from K-314, report from K-493. The story is the same. Our commanders are reporting that they are being trailed by American attack submarines moving at sustained speeds of 25, 30, even 32 knots. And yet these American boats are maintaining continuous acoustic contact. A murmur went around the room. A scientist from the acoustics lab spoke up, adjusting his glasses nervously. "That is impossible, Admiral. At 30 knots, the flow noise over the sonar dome is deafening. The Americans would be blind. They would be driving a race car with the windshield painted black." "And yet," the Admiral countered, pointing a thick finger at the map, "they are not crashing. They are not losing our boats. They are staying in the baffles of our missile submarines for days at a time. The question is, how?" The room descended into a debate that was fueled by fear. If the Americans could track Soviet boomers at high speed, the Soviet nuclear deterrent was vulnerable. The Bastion strategy, hiding submarines in home waters, relied on the assumption that American hunters would have to slow down to search. If they didn't have to slow down, they could sweep the Barents Sea in hours. 4 theories emerged from the smoke-filled room, each one desperate to explain the impossible. Theory 1. Active sonar. A senior captain from the Northern Fleet suggested that the Americans were using a new form of high-frequency active sonar. "Perhaps they are pinging us," he argued. "Short, encrypted pulses that our warning receivers interpret as background static. If they are using active sonar, they don't need to listen, they just need to see the echo. The tactical analysts shook their heads. Active sonar is a suicide note. It reveals the position of the hunter far more clearly than the target. If an American submarine were blasting active sonar all over the Barents Sea, every Soviet ship within 100 miles would hear it. The Americans were arrogant, yes, but they were not stupid. They valued stealth above all else. The reports from captains like Antonov were specific. The Americans were silent, no pings, just a shadow that wouldn't go away. Theory 2, espionage. The KGB officer in the corner leaned forward. His theory was darker and, in a way, more comforting to the naval officers because it didn't imply their equipment was inferior. They are cheating, he said. They are not tracking us acoustically. They are reading our orders. This theory had weight. The Soviet intelligence apparatus knew that their communication security was not perfect. If the Americans had broken the naval codes, or if they had a spy in the fleet headquarters, they would know exactly where a Soviet submarine was ordered to patrol. They drive to the patrol box at 30 knots because they know the destination, the KGB man argued. They wait there. When our boat arrives, they simply fall in behind. It was a plausible explanation. Indeed, unknown to the men in the room, the Walker spy ring had been selling American secrets to the Soviets for years, proving that espionage was a viable tool. It was logical to assume the Americans were doing the same, but the admiral rejected it. Codes tell you where to go, he snapped. They do not tell you when a captain decides to turn. They do not tell you when he changes depth to check a thermal layer. Antonov reports that the American matched his speed changes second for second. Espionage cannot do that. Only sensors can do that. Theory 3, non-acoustic detection. The scientists from the physics institutes proposed that the Americans had abandoned sound entirely. They suggested that the U.S. Navy had developed a way to see submarines using other spectra. Satellite detection of wake turbulence, one suggested, or perhaps thermal imaging of the reactor heat plume rising to the surface, or magnetic anomaly detectors so sensitive they can feel the steel hull from miles away. The committee reviewed the data. Thermal detection worked, but only if the submarine was shallow and the water was calm. Magnetic detection worked, but the range was measured in hundreds of meters, not miles. To track a submarine across the Atlantic using magnetic sensors, the hunter would have to be practically sitting on top of the target. None of these technologies explained how a Los Angeles-class submarine could follow a target from 10 miles back while sprinting at 30 knots. The Americans were not looking down from space. They were down there in the mud, fighting knife fights in the dark. Theory 4, the impossible reality. As the hours wore on, the theories were stripped away, leaving only the explanation that no one wanted to accept. It was the explanation that threatened the careers of every man in the room because it meant they had fundamentally underestimated the enemy. The chief engineer of the Rubin Design Bureau, the man responsible for designing Soviet submarines, finally spoke the truth that had been hanging over the table. "Comrades," he said quietly, "we must consider the possibility that the Americans have solved the flow noise problem." The room went silent. "If they are not using active sonar," the engineer continued, "and they are not reading our minds, then they must be listening. And if they are listening at 30 knots, it means they have found a way to separate their ears from their own noise." He walked to the chalkboard. He drew a crude outline of a submarine. "The noise comes from the hull," he said, tapping the chalk against the drawing. "The water rushing over the steel, the turbulence around the sail, the cavitation of the screw. If the sensor is on the hull, the sensor is deaf at high speed. It is physics." He paused, looking at the admirals. But what if the sensor is not on the hull? The concept hung there, radical and terrifying. For 70 years, sonar had been a thing attached to the ship, a dome on the bow, a hydrophone on the keel. It was part of the vessel. If they could detach the sonar, the engineer theorized, and drag it behind them, miles behind them, away from the flow noise, away from the reactor pumps, away from the screw. "A towed array," the admiral muttered. The Soviets had experimented with towed sensors, mostly for communication antennas or crude geophysical survey gear. But a tactical sonar array? A string of hydrophones delicate enough to hear a watch ticking, yet rugged enough to be dragged through the ocean at highway speeds? The engineering challenges were staggering. The cable would have to be miles long to escape the submarine's own noise footprint. It would have to transmit massive amounts of data back to the ship without signal loss. It would have to remain stable, not twisting or vibrating in the current, which would create its own noise. And the signal processing computer required to filter out the sound of the ocean from a moving sensor would need to be generations ahead of anything Soviet industry could produce. If they have done this, the KGB officer said, then our entire doctrine of speed is obsolete. The Soviet Navy had built its strategy on speed. Their Alpha-class submarines were titanium hot rods designed to outrun torpedoes. Their tactics relied on the belief that if you ran fast enough, you could break contact because the enemy couldn't track you. But if the Americans had a long ear, a sensor that could be towed in the quiet water miles behind the hunter, then the American submarine could sprint at 30 knots, while its ears glided silently in the wake, hearing everything. They could chase a Soviet boat at top speed and never lose the acoustic picture. The meeting broke up late in the night, but there was no relief in the conclusion. The Admiralty issued new orders. Every intelligence asset, every spy, every trawler was to look for evidence of this technology. They needed to know what the Americans were dragging behind their boats. The panic that gripped the Soviet Naval Command was not the panic of imminent destruction, but the cold dread of obsolescence. They had spent billions of rubles building a fleet of fast, deep-diving submarines, believing that the laws of physics protected them at high speed. Now, it appeared the Americans had engineered a loophole in physics. While the admirals in Moscow argued over the theoretical possibility, the reality was already patrolling their waters. The USS Phoenix, the boat trailing Captain Antonov, was indeed towing a thin black line through the Barents Sea. It was a piece of technology that looked like a simple rubber cable, but it was the noose that was slowly tightening around the neck of the Soviet Navy. The investigation was over. The conclusion was terrifying. The Americans had learned to separate the listener from the noise. They had built a system that allowed them to run and hear at the same time. And the Soviet Union, trapped in its doctrine of hull-mounted sensors, was deaf, dumb, and blind to the threat that was already right behind them. The answer to the riddle that terrified the Soviet Admiralty was not found in a new law of physics, nor in a magical device that could see through water. It was found in a thick, black rubber cable, roughly 3 inches in diameter, that trailed behind American submarines like a long, sensory tail. It was a piece of technology that looked unimpressive to the naked eye, miles of wire and polyurethane, but it represented the single greatest leap in underwater surveillance since the invention of sonar itself. The United States Navy designated it the TB-16 Towed Array Sonar. To the crews who operated it, it was known simply as the Fat Line. To understand why a rubber cable broke the strategic balance of the Cold War, one must revisit the fundamental paradox of submarine acoustics. For 70 years, naval architects had been trapping the sonar operators inside the same steel box that generated the noise. The hydrophones were mounted on the hull, usually in a dome at the bow. This meant that the ears of the ship were bolted just a few hundred feet away from the screaming turbines and the thrashing propeller. It was like trying to hear a whisper in a library while someone was running a vacuum cleaner in the same room. As long as the vacuum cleaner, the submarine, was running, the whisper was lost. The engineers at the Naval Underwater Systems Center asked a simple, heretical question. What if we move the ears? If the noise of the submarine is the problem, the solution is to put distance between the sensor and the source. They developed a system to unspool a long string of hydrophones from a tube in the submarine's hull. This cable would drag behind the boat, drifting in the wake. The physics of this separation were transformative. Sound intensity decreases with the square of the distance. By placing the sensors half a mile or a mile behind the submarine, the noise of the reactor pumps and the reduction gears faded into the background. The hydrophones were no longer listening to their own ship, they were listening to the ocean. Furthermore, the towed array solved the problem of flow noise. When a submarine moves at 25 knots, the water rushing over the hull creates a deafening roar that blinds hull-mounted sensors. But 2,000 feet behind the boat, the water is relatively calm. The cable slices through the sea with minimal resistance. The hydrophones inside the cable are insulated from the turbulence. They glide through a quiet environment even when the submarine pulling them is sprinting at highway speeds. This was the secret that Captain Antonov could not guess. The American submarine trailing him wasn't breaking the laws of physics, it was bypassing them. The USS Phoenix was indeed making noise at 25 knots, but its ears were a mile back, floating in the silence, listening to the Soviet boat's every move. The hardware itself was a marvel of rugged engineering. The TB-16 was housed in a long tube running along the exterior of the Los Angeles-class pressure hull. When deployed, the crew would slow the ship and let the drag of the water pull the cable out. It was a heavy, semi-rigid array designed specifically for durability. Unlike more delicate systems, the TB-16 was built to survive high-speed operations. It could be towed at speeds that would rip other sensors apart. But the cable was only half the weapon. The long ear provided the raw data, but it required a brain to understand it. That brain was the AN/BQQ-5 sonar suite. In the Soviet Navy, sonar was largely an analog art. Operators stared at oscilloscopes and listened to raw audio feeds, relying on human intuition to filter out the static. The BQQ-5 digitized the ocean. It was the first fully digital sonar system, powered by supercomputers that were, at the time, more powerful than anything available to the entire Soviet industrial sector. The BQQ-5 used a technique called beamforming. The computer would take the signals from the hundreds of individual hydrophones spaced along the towed array and mathematically combine them. By adjusting the timing of the signals, the computer could electronically steer the listening beam. It could focus on a specific slice of the ocean, ignoring noise from other directions. This allowed the sonar operators to perform frequency analysis in real time. The computer would strip away the random noise of the ocean, the waves, the rain, the shrimp, and look for man-made patterns. It hunted for specific frequencies: the 50 Hz hum of a Soviet electrical grid, the specific blade rate of a Victor third propeller, the characteristic whine of a turbopump. When the BQQ-5 locked onto a signal, it didn't just tell the operator there is a submarine. It compared the sound to a massive library of acoustic signatures stored in its memory banks. It could tell the captain, "Contact Sierra 1 is a Delta II class, hull number K424, operating at 12 knots. The integration of the towed array and the BQQ-5 computer created a tactical revolution. It fundamentally broke the geometry of the Crazy Ivan. For decades, Soviet captains had relied on the Crazy Ivan maneuver to clear their baffles. They knew that an American submarine following them would have to hide in the acoustic blind spot directly behind their propeller. To check that spot, the Soviet boat would turn violently, swinging its bow sonar around to listen to the water it had just passed through. If an American submarine was following close behind, relying on hull-mounted sonar, the Crazy Ivan was terrifying. The American captain would see the Soviet boat swinging toward him at point-blank range. He would have to slam on the brakes or dive to avoid a collision, creating noise that would betray his position. But with a towed array, the geometry changed. The American submarine didn't need to sit directly behind the Soviet propeller to stay hidden. It could trail from miles back or off to the side. More importantly, the towed array lived in the blind spot. The sensor was physically located in the baffles of the American boat, looking backward into the clear water. When Captain Antonov executed his turns in the Barents Sea, he was swinging his bow around to look for a submarine that was thousands of yards away. Meanwhile, the American towed array was drifting silently through the turn, watching the Soviet boat thrash about. To the American sonar operators, a Crazy Ivan wasn't a threat. It was a photo opportunity. It presented the broadside of the Soviet submarine to the array, allowing the computer to gather even more data on its acoustic signature. The technological dominance didn't stop with the TB-16. As the 1980s progressed, the Navy introduced the TB-23 thin line array. This was a much longer, thinner cable, essentially a wire thousands of feet long. It was more fragile than the fat line and could not be towed at high speeds, but its length gave it incredible sensitivity to low-frequency sounds. Low-frequency sound waves travel thousands of miles through the ocean. They are the bass notes of the sea. With the TB-23 deployed, an American submarine could detect a Soviet diesel boat snorkeling in the next ocean basin. It turned the Los Angeles class into a planetary listening post. The combination of these systems meant that the ocean was no longer a place of hiding for the Soviet Navy, it was a fishbowl. The impact on the crew was profound. In the control room of a Los Angeles-class boat, the sonar shack became the center of the universe. The stack of servers humming in the corner was as important as the reactor. The sonar technicians, often young men in their early 20s, became the most lethal hunters on the planet. They sat in the dark, watching waterfalls of green light, analyzing the ocean with the detachment of scientists. They learned to sprint and listen. The tactical doctrine evolved. A Los Angeles captain could sprint at 30 knots to a new patrol box, dragging the sturdy TB-16 behind him, maintaining a level of situational awareness that was previously impossible at high speed. Then he could slow down, deploy the TB-23, and listen to the entire ocean breath. This was the capability that Captain Antonov had sensed but could not comprehend. He was being tracked by a system that separated the sensation of hearing from the act of moving. The technology also had a psychological component. Because the towed array was passive, it only listened, it never pinged, the Soviet target never knew for sure if he was being tracked. He could sail for weeks, thinking he was alone, while an American computer logged his every course change and depth excursion. The first warning he would get would be the sound of a Mark 48 torpedo going active a few seconds before impact. By the mid-1980s, the long ear had become standard equipment on every attack submarine in the U.S. fleet. The technology was retrofitted onto the older Sturgeon class and integrated into the keel of every new Los Angeles. It was a force multiplier that negated the Soviet numerical advantage. It didn't matter if the Soviets had twice as many submarines if they were all deaf and the Americans could hear everything. The BQQ-5 and the towed array transformed the nature of the confrontation. It shifted the battle from a knife fight in a phone booth to a sniper duel where only one side had a scope. The Soviets were still building submarines designed to fight in the 1960s, fast, deep, and rugged. The Americans were fighting the war of the 1990s, digital, networked, and silent. But a sensor is useless without a platform to carry it. The towed array was a heavy, cumbersome piece of gear. It required a submarine with massive reserve power to drag it through the water at speed. It required a hull large enough to house the massive cable drums and the banks of computers needed to process the data. It required a ship that was fast enough to be a hunter, but quiet enough not to deafen the sensitive ears trailing in its wake. The Navy needed a new class of submarine, a fast attack, that was designed from the keel up to be the ultimate carrier for this new technology. They needed a ship that could sprint across the Atlantic to intercept a Soviet breakout, yet arrive quiet enough to deploy the array and disappear. That need gave birth to the machine that would carry the long ear into history. It was time to build the Los Angeles class. In January 1968, the United States Navy received a shock that shattered its assumptions about underwater supremacy. The aircraft carrier USS Enterprise, the first nuclear-powered carrier in history, and the fastest capital ship in the fleet, was steaming toward Vietnam. She was transiting the Pacific at high speed, a massive city of steel moving at over 30 knots. Her captain believed that at that speed, he was immune to submarine interception. The conventional wisdom held that nuclear submarines were endurance runners, not sprinters. They could stay under forever, but they could rarely sustain speeds above 25 knots. Then the sonar reports came in. A Soviet submarine had intercepted the battle group. It wasn't just lurking in an ambush position, it was chasing them. The Soviet boat, identified as a November-class nuclear attack submarine, fell in behind the Enterprise. As the carrier accelerated to 30 knots, the Soviet boat matched the speed. For 2 days, the November stayed glued to the carrier's wake, running flat out, displaying a raw horsepower that American intelligence did not believe the Soviets possessed. The implications were catastrophic. If a Soviet submarine could catch a nuclear carrier, the entire strategy of power projection was at risk. In a shooting war, that November would have simply run down the carrier and emptied its torpedo tubes into the screws. The Navy turned to Admiral Hyman Rickover. The demand was simple and non-negotiable. Build a submarine that is fast enough to escort a carrier and lethal enough to kill the Soviet fast movers. This directive gave birth to the Los Angeles class, designated SSN 688. It would become the backbone of the American submarine force, a machine designed to correct the deficit of speed while maintaining the supremacy of silence. The design process was a war between competing physics. To make a submarine fast, you need a massive power plant. To make a submarine quiet, you need heavy sound isolation. To make a submarine deep diving, you need thick, heavy steel. Trying to do all three simultaneously usually results in a ship that does none of them well. Rickover's solution was the S6G reactor. It was a pressurized water reactor derived from a plant originally designed for surface cruisers. It was huge, powerful, and capable of generating 35,000 shaft horsepower. It was a reactor designed to drive a 10,000-ton cruiser at 30 knots, and Rickover decided to stuff it inside a submarine hull. The result was a vessel of unprecedented size for an attack submarine. The Los Angeles measured 360 feet long, longer than a football field. It displaced nearly 7,000 tons submerged. It was a fast attack in the truest sense. While the top speed remains classified to this day, it is widely acknowledged that a 688 can exceed 32 knots submerged, with some accounts suggesting speeds closer to 37 knots in a sprint. But while the Americans were building their fast steel shark, the Soviet Union was building a monster of a different breed. Intelligence reports began to filter out of the USSR regarding a new project, designated Project 705 Lyra by the Soviets and the Alpha class by NATO. The specifications of the Alpha read like science fiction. The Soviet engineers, unconstrained by the safety margins demanded by Western navies, had decided to break every rule of naval architecture. They abandoned steel entirely. The hull of the Alpha was forged from titanium alloy. Titanium is lighter than steel and non-magnetic, making the submarine invisible to magnetic anomaly detectors. More importantly, it is incredibly strong. The Alpha was designed to dive to depths exceeding 2,000 feet, far below the crush depth of any American torpedo then in existence. But the propulsion was even more radical. The Soviets installed a liquid metal-cooled reactor. Instead of water, the core was cooled by a molten lead-bismuth alloy. This allowed the reactor to be incredibly compact and operate at extreme temperatures, generating immense power for its size. The performance of the Alpha was terrifying. It could reach speeds of 41 to 45 knots underwater. It was essentially an underwater interceptor aircraft. It could accelerate from 0 to top speed in less than a minute. In a dogfight, an Alpha could theoretically outrun an American torpedo. When the Alpha first appeared, panic rippled through the Pentagon. The U.S. Navy feared they had been checkmated. How do you fight a submarine that is faster than your weapons and can dive deeper than your hull can survive? The answer lay in the philosophy of the two nations. The Soviets had built a hot rod, fast, exotic, and dangerous to its own crew. The Americans built a sniper, patient, reliable, and invisible. The Los Angeles class could not outrun an Alpha in a straight drag race. But the American designers bet everything on the idea that the race would never happen, because the Alpha would be dead before it knew the race had started. The weakness of the Alpha was its noise. The liquid metal reactor required pumps that had to run constantly to keep the coolant from freezing solid. The titanium hull transmitted vibration. At 40 knots, the Alpha was the loudest thing in the ocean. It was a roaring cow, detectable from hundreds of miles away. The Los Angeles, by contrast, was a masterpiece of acoustic engineering. The heart of this stealth was the propeller. For decades, propellers had been the Achilles heel of submarines. As a blade spins, the tip moves faster than the hub. At high speeds, the pressure on the trailing edge of the blade drops so low that the water literally boils. Vacuum bubbles form and collapse violently. This is cavitation. It creates a noise like a jackhammer. To solve this, the Navy and its contractors engaged in a secretive, highly classified effort to redesign the geometry of the screw. They utilized the most advanced computer modeling of the 1970s. The result was the skewback propeller. Instead of the traditional paddle-shaped blades, the Los Angeles propeller featured 7 long, graceful blades that curved back like scimitars. This shape allowed the blade to slice into the water gradually, distributing the pressure load. It delayed the onset of cavitation. A Los Angeles-class boat could reach tactical speeds 15 or 20 knots without cavitating. It could move fast and stay silent. Manufacturing this propeller required a level of industrial precision that bordered on art. The bronze alloy had to be cast and then machined to tolerances measured in thousandths of an inch. A single imperfection, a burr the size of a grain of sand, could create a singing propeller that would betray the boat. The propeller was so sensitive that when the submarines were in dry dock, the screw was always covered with a tarp. It was forbidden to photograph it. It was a state secret made of bronze. Inside the hull, the Los Angeles was packed with the rafting technology that isolated the S6G reactor from the steel skin. The hull was coated in anechoic tiles. The result was a platform that combined the horsepower of the Enterprise escort requirement with the stealth of a spy ship. When the USS Los Angeles was commissioned on November 13, 1976, the balance of power shifted. The Soviets had the Alpha, a titanium marvel that could do 42 knots. But the Los Angeles could do 30-plus knots and deploy the towed array sonar. This was the synergy that the Soviets had missed. The speed of the Los Angeles allowed it to sprint to a patrol box, intercept a target, or escape a weapon. But its silence and its sensors allowed it to see the enemy first. In the acoustic war, the equation was simple. He who detects first wins. If an Alpha and a Los Angeles were in the same ocean, the Los Angeles would hear the Alpha screaming along at 30 knots from 50 miles away. The American commander would slow down, deploy the towed array, refine the solution, and launch a Mark 48 torpedo. The Mark 48 was the other half of the American response. Designed specifically to kill deep-diving Soviet threats, the Mark 48 was a heavyweight acoustic homing torpedo. It was wire-guided, meaning the submarine could steer it remotely. It had a reach of more than 20 miles and a speed of 55 knots. It could dive as deep as the Alpha. The Alpha might be fast, but it wasn't faster than a Mark 48. And because the Alpha was deaf at high speed, it would never hear the launch transient. The Soviet captain would be running blind, thinking he was the hunter, right up until the moment the warhead broke his titanium pressure hull. By the early 1980s, the shipyards at Newport News and Groton were churning out Los Angeles-class boats at a furious pace. Eventually, 62 of them would be built. It remains the largest class of nuclear submarines ever constructed. They swarmed the Atlantic and the Pacific. They were not just defensive weapons protecting aircraft carriers, they were offensive hunters. Their mission was to go north under the ice into the Soviet bastions. They were designed to find the Soviet missile boats, the Typhoons and Deltas, and shadow them. This brings us back to the panic in the Soviet Admiralty. They realized that the Americans had built a fleet of 62 capital ships that were acoustically superior to anything in the Soviet inventory. The Los Angeles class was fast enough to keep up with any target and quiet enough to disappear at will. The fast attack had arrived. It was a platform that could carry the long ear into the enemy's backyard. The engineering gap had become a strategic chasm. The Soviets had bet on titanium and brute force. The Americans had bet on precision and information. And in the silent, dark waters of the Cold War, precision was winning. But building the machine is only the first step. You have to use it. And the specific use of the Los Angeles class, the aggressive, forward-deployed trailing of Soviet submarines, would lead to some of the most tense and dangerous confrontations of the 20th century. The theoretical advantage was about to be tested in a game of underwater chicken that would last for 44 days. The engineering triumph of the Los Angeles class and the towed array sonar system created a capability that was unprecedented in the history of naval warfare. But capability is potential. Operations are kinetic. To turn the blueprints and the rubber cables into strategic dominance, the United States Navy had to do something incredibly dangerous. They had to send these machines into the enemy's backyard and prove that they could stay there. This operational doctrine was known by various code names over the years: Holy Stone, Pinnacle, Bollard, Barnacle. The names changed, but the mission remained consistent and terrifyingly simple. Penetrate the Soviet bastions, find a ballistic missile submarine carrying nuclear warheads, and shadow it. Trailing is a deceptive term. It implies a passive following, like a detective tailing a suspect on a city street. In the underwater realm, trailing is an act of extreme aggression. It involves placing a 4,000-ton attack submarine within lethal range of a target and matching its every move, turn for turn, depth change, for weeks at a time. It requires a level of intimacy that borders on the violation. The hunter lives in the prey's acoustic shadow, breathing the same water, listening to the enemy crew flush toilets and open hatches, knowing that a single mistake leads to collision or detection. The most legendary demonstration of this capability occurred in 1978, involving a submarine that predated the Los Angeles class but utilized the same revolutionary towed array technology. The USS Batfish, SSN 681, a sturgeon-class boat, was patrolling the Norwegian Sea when her sensors picked up a faint, rhythmic thumping. The computer analyzed the frequencies. It wasn't a whale. It wasn't a trawler. It was a Soviet Yankee-class ballistic missile submarine, departing its base on the Kola Peninsula. The Yankee was the Soviet equivalent of the American George Washington class. It carried 16 liquid-fueled missiles aimed at the cities of the American East Coast. Its mission was to transit the Greenland-Iceland-UK gap, enter the deep Atlantic, and disappear into a patrol box where it would wait for the order to end civilization. The Batfish moved to intercept. The American captain maneuvered his boat into the acoustic blind spot of the Soviet vessel, deploying the long black tail of the TB-16 towed array. The trail began. For the first few days, the game was tense but manageable. The Soviet commander followed standard doctrine. He moved at a patrol speed that minimized noise. He executed periodic crazy Ivans, swinging his ship violently to check his baffles. Each time, the Batfish, listening through the towed array drifting far behind, watched the maneuver unfold on the sonar screens and adjusted course to stay clear. Then the North Atlantic decided to intervene. A massive winter storm system rolled off the ice cap. On the surface, the waves built to 40 feet. Winds screamed at 70 knots. Even hundreds of feet down, the ocean was in turmoil. The background noise, the ambient sound of the sea, rose to a deafening roar. The crashing of waves and the cavitation of the surface water created a wall of static that blinded the sensors. In the acoustic chaos, the Batfish lost contact. The Yankee slipped away into the storm. This is the nightmare scenario for a hunter-killer. A nuclear-armed adversary is loose in the Atlantic, and you have lost him. But the American captain trusted his technology. He knew the Soviet boat had to follow a specific logic. He knew the geography of the ocean floor. The Batfish began a search pattern. The sonar operators filtered the storm noise, looking for the specific mechanical signature of the Yankees' propulsion plant. They found it in less than 4 hours. In millions of square miles of angry ocean, the American submarine reacquired the needle in the haystack. They closed the distance. They reestablished the trail. For the next 44 days, the Batfish lived in the Yankees' shadow. They followed the Soviet boat all the way into the deep Atlantic. They followed it as it entered its patrol box. They sat there, hovering silently, while the Soviet crew conducted their drills. The American crew recorded everything. They taped the sound of the missile tube hatches being tested. They recorded the maintenance cycles of the reactor pumps. They intercepted the communications traffic. When the Yankee finally turned for home, its patrol complete, the Batfish followed it back. Only when the Soviet submarine approached its own territorial waters did the American boat break contact and turn away. The intelligence value of the mission was incalculable, but the strategic message was even louder. The Batfish had proven that a Soviet missile submarine could be held at gunpoint for its entire patrol. In a shooting war, that Yankee would have been destroyed before it could launch a single missile. The 16 cities it targeted were safe, not because of a missile defense shield, but because of a silent hunter swimming in its wake. As the Los Angeles class entered service in mass numbers throughout the 1980s, this feat was replicated on an industrial scale. The Navy had built 62 of these fast attack boats for a reason. They swarmed the Atlantic. They pushed into the Barents Sea. They turned the Batfish's exceptional performance into a standard operating procedure. Every Soviet ballistic missile submarine that left port was effectively tagged and tracked. The operational advantage was defined by the detection range. Under favorable conditions, an American submarine towing a long array could detect a Soviet boat at ranges of 50 to 100 nautical miles. The Soviet boat, relying on hull-mounted sonar and plagued by its own self-noise, could rarely detect the American beyond 10 or 20 nautical miles. This asymmetry meant that American commanders lived in a world of information dominance. They could see the enemy from the next county. They could maneuver to the optimal attack position, the geometry of the kill, hours before the Soviet captain even looked at his sonar screen. But playing tag with 19,000-ton steel tubes in pitch darkness is inherently dangerous. The margin for error is measured in seconds, and sometimes the physics of momentum overrode the skill of the crews. In October 1986, the USS Augusta, SSN 710, a Los Angeles-class boat, was on patrol in the North Atlantic. She was testing a new, highly advanced sonar system. Her captain was aggressive. The target was a Soviet Delta-class ballistic missile submarine. The Augusta was trailing closely, perhaps too closely. The ocean acoustics played a trick, a sudden thermal layer or a baffle clearing maneuver that wasn't detected in time. The two submarines collided. It was not a catastrophic, hull-shattering impact, but a grinding, terrifying collision of titans. The Augusta reportedly struck the Soviet boat with her bow. The Delta, oblivious until the impact, continued on. The Augusta suffered significant damage to her sonar dome, the fiberglass nose that houses the listening sphere. She limped back to Groton for repairs costing millions of dollars. The Navy issued a tight-lipped statement about a collision with an underwater object. But inside the service, the message was clear. The game was real. We are touching them. Years later, in February 1992, just as the Cold War was fading, the USS Baton Rouge, SSN 689, was participating in a surveillance mission near Severomorsk, the Russian Northern Fleet headquarters. She was tracking a Sierra-class attack submarine, the Kostroma. The Baton Rouge was shallow, at periscope depth. The Kostroma was below her. The Russian boat began to surface. The American captain tried to evade, but the geometry was fatal. The Kostroma came up underneath the Baton Rouge, her sail slicing into the American hull. Both submarines survived, but the damage was extensive. The Baton Rouge was eventually decommissioned due to the structural stress of the impact. The incident sparked a diplomatic firestorm, with the Russians producing debris from the American boat found on their deck. It was a stark reminder that even as the political war ended, the underwater war remained a contact sport. Throughout this entire period, the Soviet leadership was aware of the catastrophe unfolding in their oceans, and they knew it because they had bought the information from John Walker. The Walker spy ring had provided the Soviets with the operational orders of the U.S. Navy. They knew that the Americans were conducting these trailing operations. They knew the code names. They knew the patrol sectors. But this knowledge was a poisoned chalice. Knowing you are being followed is useless if you cannot find the follower. The Walker intelligence confirmed the worst fears of the Soviet Admiralty. It told them that their Bastion strategy was leaking. It told them that their Typhoon and Delta submarines, the guarantors of their national survival, were being tracked from the moment they cleared the harbor nets. The Soviets tried to adapt. They developed the Victor III with its own towed array pod on the stern plane, a direct attempt to copy American technology. They poured resources into the Akula class, but they were trying to close a gap of 30 years in a single decade. The tactical reality in the control rooms of the Los Angeles fleet was one of quiet, professional arrogance. The crews knew they were superior. They knew their gear was better. They trusted the fat line trailing behind them. They developed a culture of aggressive hunting. They practiced snapshots, firing torpedoes on short notice. They practiced navigating under the Arctic ice, using upward-looking sonar to find the leads, patches of open water where they could surface. The Mark 48 torpedo became the ultimate arbiter of this dominance. With a speed of 55 knots and wire guidance that allowed the fire control officer to steer it like a remote-controlled plane, the Mark 48 could run down even the fastest Soviet targets. Against an Alpha, the American tactic was simple: shoot him in the face before he can accelerate. Against a Typhoon, the tactic was to break its back before it could launch its missiles. By the late 1980s, the Atlantic Ocean had become a NATO lake. The Soviet Navy, once aspiring to blue water dominance, was boxed in. They could not move without being seen. They could not hide. The psychological pressure on Soviet commanders was immense. They went to sea knowing that somewhere back there, in the baffles, an American was writing down their every move in a logbook. The 44-day shadow of the Batfish had become the permanent state of affairs. The Los Angeles class had achieved what no other naval force in history had accomplished. They had rendered the enemy's capital ships functionally irrelevant before the war even started. This dominance had consequences that reached far beyond the water. It forced the Soviet Union to spend money it didn't have on countermeasures that didn't work. It forced them to keep their fleet close to home, abandoning the global power projection that defined a superpower. And ultimately, it broke the will of the Soviet Admiralty. They realized that in the event of a nuclear war, they would lose. Their second strike capability would be strangled in its crib. The underwater checkmate was complete, but as the 1980s drew to a close, a new threat emerged, not from the ocean, but from a corporate boardroom in Japan. The technological wall that protected American dominance was about to be breached, not by Soviet scientists, but by a traitorous sale of milling machines. The Los Angeles class had won the War of the 80s, but the War of the 90s was about to get much quieter. By 1987, the Atlantic Ocean had effectively become a NATO lake. The vision of Admiral Sergei Gorshkov, a blue-water Soviet Navy capable of challenging the United States on the high seas, was dying a quiet, suffocating death beneath the waves. The cause of death was not a lost battle or a political treaty, but a simple, brutal calculation of acoustics. The Soviet Admiralty realized that if they sent their ballistic missile submarines into the open ocean, they would die. The Los Angeles-class submarines, now numbering over 40 hulls in the water, had created a perimeter of silence that the Soviets could not penetrate. The ghost ships were everywhere. They were guarding the Greenland-Iceland-UK gap. They were patrolling the approaches to Murmansk. They were waiting off the coast of Vladivostok. Faced with the reality that their strategic deterrent was vulnerable, the Soviet leadership ordered a historic retreat. They abandoned the concept of global patrol. They instituted the bastion strategy. Instead of hiding in the vastness of the Atlantic, Soviet missile submarines, the Deltas and the massive Typhoons, were ordered to stay home. They would patrol only in the Barents Sea and the Sea of Okhotsk, bodies of water that were essentially Soviet lakes. Here, they could be protected by rings of surface ships, minefields, and land-based aircraft. They would hide behind a wall of steel because they could no longer hide behind a wall of silence. This was a victory of immense strategic proportion for the United States. By forcing the Soviet Navy into a defensive crouch, the Los Angeles class had effectively neutralized the threat to the Atlantic sea lanes. If World War III had broken out, the Soviet Navy would have been too busy protecting its own backyard to stop the American convoys reinforcing Europe. The submarine war was won before the first torpedo was fired. But in the final years of the decade, a betrayal occurred that would threaten this dominance and reshape the future of underwater warfare. It did not come from a spy ring or a defecting scientist. It came from a corporate boardroom. In 1987, intelligence analysts began to notice a disturbing trend. The new Soviet Akula-class attack submarines were becoming quieter, much quieter. The blade rate noise, the telltale thumping of the propeller that had betrayed Soviet boats for 30 years, was disappearing. The investigation led to a shocking discovery. A subsidiary of the Japanese giant Toshiba, working with the Norwegian company Kongsberg, had illegally sold advanced 9-axis computer-controlled milling machines to the Soviet Union. These were the machines the Soviets had desperately lacked. They were capable of carving complex, skewed propeller blades with the same precision as the Americans. For a few $1 million, Toshiba had sold the crown jewels of Western naval supremacy. The impact was immediate. The Soviets used the machines to manufacture new propellers for their Victor III and Akula-class boats. The acoustic gap, which had been a chasm, began to narrow. The Akula became a formidable adversary, a shark that had finally learned to stop thrashing. Senator John Hines called it one of the most damaging technology transfers of the Cold War. American submarine commanders noticed the difference immediately. The easy detections were gone. The ocean was getting quieter, and therefore more dangerous. However, the technology arrived too late to save the Soviet Union. The economic cost of trying to match the Reagan administration's military buildup was breaking the back of the Soviet economy. The Kremlin had poured billions of rubles into the Typhoon program, the Akula program, and the Bastion defenses. They were building titanium hulls and liquid metal reactors while their citizens stood in line for bread. The Los Angeles class had played a crucial role in this economic warfare. By rendering older Soviet submarines obsolete, they forced the USSR to spend money it didn't have on new designs. The ghost ships didn't just hunt submarines, they hunted the Soviet treasury. On November 9, 1989, the Berlin Wall fell. 2 years later, the red flag over the Kremlin came down. The Soviet Union ceased to exist. The massive fleet that Gorshkov built was left to rot. The Typhoons, the largest submarines ever built, sat rusting at the piers in Severomorsk, too expensive to operate. The Alphas, the titanium hot rods, were decommissioned and scrapped. The threat that had justified the existence of the Los Angeles class evaporated overnight. But the legacy of the 688s remained. They had held the line during the most dangerous years of the Cold War. They had proven that in the domain of high technology, precision beats brute force. Years after the end of the conflict, Captain Viktor Antonov, the man who had been chased through the Barents Sea in 1983, learned the truth about his pursuer. The ghost that had followed him for 6 days, tracking him through Crazy Ivans and depth excursions, was the USS Phoenix, SSN 702, a Los Angeles-class boat out of Norfolk. Her captain had held contact for 17,000 nautical miles of patrol track. The Phoenix had been close enough to photograph Antonov's submarine through the periscope, close enough to record the sounds of his crew working, close enough to put a Mark 48 torpedo into his engine room before he ever opened a missile tube. The ghost was real. Today, the Los Angeles class is fading into history. Of the 62 boats built, many have been recycled, their reactor compartments buried in the desert at Hanford alongside the Seawolf and the Jack. They are being replaced by the Virginia class, submarines designed for a new world of literal warfare and drone operations. But the lesson of the Los Angeles class endures. It taught the world that the ocean is not a place of hiding for those who are loud. It proved that a navy that cannot master the physics of sound is a navy that cannot survive. The Cold War was a conflict defined by shadows and silence. It was won by young men sitting in dark rooms, staring at green screens, listening to the static of the earth. And it was won by a machine that could sprint at 30 knots and hear a pin drop in the next county. The Los Angeles class was the ultimate predator of the 20th century. It cleared the ocean. It broke the will of an empire, and it did it all without ever being seen. The story of the Los Angeles class and the towed array sonar is a masterclass in asymmetric advantage. It wasn't just that the American boats were better, they were operating on a different plane of sensory reality. While the Soviets were fighting a kinetic war of speed and depth, the Americans were fighting an informational war of signal and noise. This technological dominance had a profound stabilizing effect. By making the Soviet submarine force vulnerable, the Los Angeles class paradoxically made the world safer, forcing the Soviets into a defensive posture rather than an offensive one. It is a reminder that in the calculus of deterrence, the most dangerous weapon is the one your enemy knows is there but cannot find. The Los Angeles class didn't just win the Cold War at sea, it defined the modern era of submarine warfare. Every submarine built today by any nation is measured against the standard set by the 688s. They were the ghosts that haunted an empire to death. Thank you for spending part of your day with us to uncover these hidden files. If this deep dive into the silent war added value to your understanding of history, we'd be honored to have you with us for the next journey. Until next time, stay curious and take good care.